If you have ever gazed up at the moon and wondered what secrets it might be hiding, get ready to embark on a journey that will forever change the way you look at our closest celestial neighbor. Today, we'll unravel some of the greatest geological mysteries of the moon. From its violent origins and the scars that mark its surface, to the surprising evidence that suggests the moon may not be as geologically dead as we once believed. Prepare to explore beyond what textbooks have told us and discover a story billions of years in the making. Imagine a world frozen in time, a silent witness to the chaos of the early solar system. No atmosphere to erode its features, no shifting tectonic plates to erase the past. The moon is a natural museum, preserving both cataclysm and calm in stone. Look close, and you will see giant impact craters, evidence of cosmic collisions, vast, dark plains that stretch across the surface like ancient seas, and winding channels, remnants of fiery rivers that once flowed in a world thought to be dormant. But how did these features form? And what do they tell us about the moon's history? Is it possible that beneath its seemingly lifeless surface, the moon still hides signs of recent geological activity? Let's begin our journey into the unique geology of the moon. To really understand the moon, we must delve into selenology, the science of lunar geology. The moon's geology is strikingly different from Earth's. First, it lacks a true atmosphere, meaning there's no wind or rain to wear down its features. There is no free oxygen or liquid water, and crucially, there are no tectonic plates shifting and recycling the crust. This makes the moon a rare kind of time capsule, where the evidence of ancient events is preserved, sometimes almost unchanged, for billions of years. Go back 4.5 billion years, and the moon was a molten sphere, what scientists call a primordial magma ocean. As it cooled, heavier minerals sank towards the center, forming the mantle and core, while lighter minerals rose to the surface, creating a thick crust of a rock called a northocite. This crust, which makes up the moon's bright highlands, is about 50 kilometers thick in places. Chemical analysis reveals further secrets. The dark plains, known as Maria, are rich in iron and titanium, while the highlands contain more aluminum and calcium. These differences are not merely about color, they are the fingerprints of the moon's fiery and tumultuous past. No discussion of lunar geology would be complete without talking about impact craters. The moon's surface is a battlefield, pockmarked with scars from billions of years of collisions with asteroids and comets. These craters come in all sizes, from simple bowl-shaped ones only a few kilometers across to complex, terraced craters with central peaks and enormous basins spanning hundreds of kilometers. Each impact crater forms in 3 stages. First is contact, when an object slams into the lunar surface at incredible speed. Next comes excavation, as rock and dust are blasted outward, creating the crater rim and rays of ejected material. Finally, modification, when the new crater's steep walls collapse inward. And, in larger craters, a central peak rises from the rebound. Some of the moon's most famous craters, like Tycho and Imbrium, are evidence of catastrophic impacts. Around 3.9 billion years ago, the moon endured a period known as the Late Heavy Bombardment. During this time, it was struck again and again, erasing earlier features and creating a dense tapestry of craters. Scientists use the number and density of these craters to estimate the relative ages of different regions. Older highlands are heavily cratered, while younger Maria have far fewer scars, having been resurfaced by later volcanic eruptions. But what about those dark maria, the seas that we see from Earth? Despite their name, these are not bodies of water, but vast plains of basalt, formed by ancient volcanic eruptions. Lava once welled up from deep inside the moon, flooding giant impact basins and creating the smooth, dark surfaces we see today. Maria cover about 16% of the moon's surface, mostly on the side facing Earth. Lunar basalt is quite different from its earthly cousin. It contains much more iron and titanium, and almost no water. Most of these volcanic eruptions happened between 3 and 3.5 billion years ago, but recent discoveries have changed our understanding. Samples brought back by China's Chang'e 5 mission suggest that some lunar basalts are as young as 2 billion years old, much more recent than previously believed. This evidence forces us to rethink the moon's volcanic history. Why are most maria located on the near side of the moon? Scientists once thought that the Earth's gravity or differences in crust thickness were responsible, but recent data points to concentrations of heat-producing elements like potassium, rare earths, and phosphorus, collectively known as creep, beneath the near side. These elements may have kept parts of the lunar mantle hot enough for volcanic activity to last much longer than elsewhere. Besides the maria, the moon's volcanic past has shaped other fascinating landscapes. Sinuous rills, such as Hadlai Rill, meander across the surface like dried-up rivers. But these are not carved by water. They are collapsed lava tubes, or channels, testifying to the moon's once active volcanoes. Some volcanic domes, like the Gruithuisen domes, suggest eruptions of unusually thick, sticky lava. Perhaps most astonishing are the irregular mare patches like Ina, which look remarkably young, possibly only 100 million years old. Even younger are tiny volcanic glass beads, also discovered by Chang'e 5, which may be at as little as 120 million years old. These findings suggest that the moon may have remained geologically active much more recently than we ever imagined. The story of the moon's surface is one of interplay between impact and volcanism. Giant basins, blasted out by colossal impacts, became natural reservoirs for lava. In some cases, rising magma fractured the floors of older craters, creating networks of cracks and sometimes flooding the craters entirely. The contrast between the heavily cratered highlands and the smoother maria is a record of these cycles. Violent impacts followed by waves of volcanic renewal. Our understanding of the moon wouldn't be possible without decades of exploration. Early robotic missions like Lunar and Ranger, followed by the iconic Apollo missions, brought back nearly 400 kilograms of lunar samples. These rocks and soils have been invaluable, confirming theories about the moon's magma ocean, volcanic maria, and the impact origin of craters. Modern missions, including NASA's Lunar Reconnaissance Orbiter and China's Chang'e series, are mapping the surface in unprecedented detail and collecting new samples, keeping the spirit of discovery alive. Yet, many mysteries remain. What exactly is the moon's origin, given the uncanny similarity between Earth and lunar rocks? How recently did its volcanic activity end? And what about the water ice hiding in permanently shadowed craters at the poles? Could this be a resource for future explorers? The moon is not just a cold, lifeless rock. It is a living archive, a silent storyteller bearing witness to the history of our solar system. Every rock, every crater, every lava flow tells a tale of fire, impact, and transformation. As we stand on the threshold of a new era of lunar exploration, fresh discoveries await, each one bringing us closer to understanding not just the moon, but our own place in the cosmos. The next great revelation could be just around the corner. What do you think we'll discover next on the moon? Stay curious, keep exploring, and join the adventure as humanity continues to unlock the secrets of our mysterious neighbor.